Started. Perfect.
Sounds good.
Hi, everyone. Today, we're super fortunate to have Andrew Wilson delivering, I think, the penultimate lecture of the NYU AI School. Andrew is an assistant professor at the Center for Data Science and Quant Institute at NYU. He's a super important member of our community, just joined from CMU. He's interested in developing flexible, interpretable, and scalable machine learning models that often involve deep learning, Gaussian process, and kernel learning. His work has been applied to a ton of different areas, like time series, vision, NLP, kind of all the domains you can imagine. I think his methods have been applied to. We're super fortunate to have Andrew here to lecture us today about Bayesian machine learning. Again, if you have questions, please post in the chat, and I'll be monitoring, and Andrew will be monitoring, so I think will be covered there. Cool. So thanks, Andrew, and feel free to take it away.
Thanks so much. I'm really excited to be here and to meet you all. And I'm going to be doing this presentation essentially stream of consciousness on the whiteboard. And so that means we can adapt it as you ask questions or have various requests. I'd like to have the lecture actually kind of organically evolve with the audience. And for that reason, it's particularly important, I think, to have a lot of good interaction. So really don't be shy at all about asking any question, regardless of whether you think it seems stupid or not. Any question is a good question. And initially as well, feel free to just unmute yourself. If things get crazy, post a chat, etc. But for now, feel free to just like unmute and ask a question as soon as you have it. And we can also, of course, take questions at the end, but I think it's often better just to ask questions as soon as there might be some confusion. So a little bit of background, I guess, on me. So I did my undergrad in math and physics at UBC in Vancouver. I'm Canadian. And I didn't know anything about machine learning at the time. I don't want to date myself too much, but machine learning also wasn't nearly as much on the radar then as it is now either. I was interested in theoretical physics, in understanding properties of black holes and unifying gravity and quantum mechanics and things like this. But it didn't seem like there were that many sort of career options in that area. And so I wasn't really sure what I wanted to do. I really loved math, but I didn't necessarily want to do graduate school in math. So I felt a bit lost, honestly, and I actually just applied to medical school kind of randomly, and I wasn't expecting to be admitted, but I was, and this sort of presented me with a weird problem because I wasn't sure I wanted to do sort of medicine either, even though it seemed like a stable career path. And so I kept deferring my admission, basically. I was still doing undergrad in physics until I realized, okay, well, I really love this physics and learning more about science, and I just want to keep doing that for a bit longer. And at some point, maybe I'll try to merge that with my interest in medicine. So for my senior project in undergrad, I tried to look for things that were connected to medicine, like medical physics. And there was this interesting project being developed at a particle accelerator laboratory called Triumph in Vancouver. It's the biggest cyclotron in the world. And the project was about building a new type of positron emission tomography device. So that's a functional imaging device. So you've probably heard of things like CT scans, MRIs, and so on. Functional imaging allows you to see things like metabolic activity, which are actually related to things like thought processes. This new device had been developed using entirely different physical principles. So it was a very exciting project. And everything needed to be done from scratch. And it was actually making use of isotopes and stuff like that that could be produced through this cyclotron and just transported immediately underground to the facility where this device was being built. And my advisor for this project, who was a physicist, he wasn't at all a statistician or a computer scientist, just suggested I read about these things called neural nets, which was interesting because he was kind of like, so out of date at that point that he was thinking neural nets were interesting. At that point in the mid-2000s, neural nets were really out of favor in the mainstream machine learning statistics CS communities. But I found these old books by Bishop in the 90s, actually, not the 2000s Bishop. And it just seemed to be a really exciting and interesting area that I wasn't really that aware of. Like I'd heard of classical AI, which was about symbolic logic and things like this. And it seemed to be sort of more like philosophy to me. And I thought it was interesting, but it wasn't something I wanted to really do as a career. Whereas this seemed sort of like applied math with virtually any kind of application and really a lot of freedom to kind of really follow your interests and to blend together all sorts of different interests. So it was very exciting just to kind of discover this discipline. And at that point, I decided, okay, well, I want to keep doing this a bit longer. It turned out neural nets were actually a really good approach to that problem, even though when I sought out sort of expert advice at the time, I was very much discouraged from following the neural net approach. So I then did my PhD at the University of Cambridge in the United Kingdom. I was sort of kind of excited to travel somewhere very different and have those new experiences. And my group there was very focused on an area of machine learning called Bayesian nonparametrics. And so that field is very excited about really building almost models with an infinite number of parameters, sort of really, really flexible models alongside a really principled representation of uncertainty. So using these things called stochastic processes basically to model the world. And it's a fairly different actually paradigm for understanding model construction and generalization. I'll try to convey some of that to you in this lecture. That will be kind of the primary purpose of this lecture. And there I worked on these models called Gaussian processes, and they were very philosophically interesting, but they couldn't be applied to a lot of problems at the time due to various computational constraints and other constraints associated with modeling choices, which were actually quite difficult to make manually. And so I became kind of interested in how we could actually address both of these questions at once. How do we resolve scalability and what's called kernel selection for Gaussian processes? And in order to approach those questions, I sort of taught myself a lot of background in an area called scientific computing, which was something I actually took a course on in undergrad that I thought was interesting, but I never realized it would be relevant for things that I would be doing in my career and my research. And it turned out to be extremely relevant. In many ways, it's just sort of linear algebra in practice on a computer. And a lot of machine learning from a foundational perspective is linear algebra. And so I was sort of teaching myself about scientific computing. And around that time, I moved to CMU. And this was sort of an interesting environment, very different from the environment at Cambridge. So Cambridge at that time in that group was very, very specialized on building Bayesian nonparametric methods. And that was interesting in the sense that you would see these passionate debates about topics that most people wouldn't even sort of understand. And they might be very, very specialized. There might be disagreements between sort of like subjective and objective viewpoints of Bayesian methods. And so it wasn't just sort of, there's sort of different levels of being Bayesian. You're sort of Bayesian, and then you're sort of Bayesian nonparametric, and then maybe you're like subjective Bayesian nonparametric. And it was just very, very intellectually interesting to see these kinds of arguments and how people really cared fundamentally about a first principles sort of understanding of how we should be building intelligent systems. At CMU, it was different in the sense that it was a very, very big department. So there were lots of faculty working on lots of different topics, and you get a much kind of broader view of the field. You also are more immediately connected to a lot of different applications. And so there are various ways to do kind of what's called core machine learning research. Either you sort of think very abstractly about problems associated with various methods and try to resolve those problems, and hopefully it'll have lots of applications. Or there's a particular scientific problem and you're trying to kind of throw anything at it to solve that problem, and that will kind of inspire methodological innovation. I think both perspectives are quite valuable. One isn't more important than the other. And in fact, I actually kind of prefer the sort of former approach in many cases, but I was exposed to the latter approach, a lot of really interesting problems at CMU. And that also sort of helped sort of shape the way that I thought about model construction. And then I moved to Cornell, and I collaborated with a lot of amazing people there and learned a lot from them and their different styles of working. And I also sort of broadened the types of questions I was interested in at that point very significantly. So I started thinking a lot about deep learning, about how to train deep neural nets a lot more effectively, about these things called loss landscapes associated with training the neural net. So you have some kind of what's called objective function that you often want to maximize to learn the parameters of a deep neural net. And that objective function has all sorts of interesting geometric properties that affect things like the performance of the model that you get after training. And so I became quite interested in those questions, also interested in NLP and vision and many other applications. And then I moved to NYU, and I've been kind of continuing in many of these directions. And I've also started to become quite excited about combining some of the things I was thinking about a long time ago when I was doing physics with machine learning. So using physics inspiration to build new methodology in machine learning, but also developing machine learning models that will be really interesting for solving physical problems. I'm still sort of fundamentally very excited about scientific discovery, sort of a model being able to tell us something that we didn't know before about a given problem that will have some kind of scientific relevance. Often a lot of the magic in science is behind the theory, like say the theory of general relativity, telling us that time is not absolute, that space and time are connected, things like this, rather than maybe a very specific application of that theory like GPS, even though that's also interesting. Okay, so with that, I will start with a question. So let's suppose, and let me know if you can't see what I'm writing on the board. Let's suppose that we have, great. Some CO2 concentrations that we're measuring as a function of time. And they look a bit like this. And we'll consider 3 different modeling choices to try to fit these data. So we'll specify that y of t is equal to a0 plus a1t. So that would just be a straight line with a slope of a1 and an intercept of a0. And we would just try to learn those parameters a0 and a1 to sort of fit this curve. So maybe we can get this rising trend. We have another model. Which is a 3rd order polynomial. So a0 plus a1t plus a2t squared plus a3t cubed. And we're going to do the same kind of thing. We're just going to try to learn these parameters, these AIs, in order to try to fit these observed data points. And we have a 3rd model. Which now has 10,000 of these parameters. So it's or 10,000 plus 1 of these parameters. It's a huge polynomial. And again, we're going to try to fit these AIs to match the data and then make predictions into the future. So maybe this point here is at 2020, and we want to make predictions up until 2025 or something like that. So if you were faced with making one of these 3 choices, which one would you make? So just in the chat, enter 1, 2, or 3. Don't think about it too much, just be reactive. Which one would you go with in this setting? Mm-hmm. Great, yeah. So I see a lot of 2s, a 1, some explanations. So does anyone want to explain why they chose what they did? So I see one. Go ahead, yeah.
So I think most of us have the same reasoning behind why we chose 2. Mm-hmm. And it's probably because 3 seems too complicated for a period of time like this. Mm-hmm. And it might involve too many intricacies that could just cause problems down the line. And then perhaps 1 is too simple for something like carbon emissions. So we feel that maybe 2 is probably the best option here.
Mm-hmm. Yeah, I think that's very reasonable. It's good to see all these explanations. So it seems like generally most people are thinking along the lines that you described, that 3 might overfit. And would someone like to explain what it would mean to overfit?
Like the model would end up satisfying all the data points like in a very detailed manner. But if we were to try and like generalize to further points which are not in this set, it would fail. Mm-hmm.
Yeah, that's a good, concise description of overfitting. So that seems to be the worry about 3. And then the worry about 1 is that maybe we'll miss some of the interesting structure. Like maybe we'll get this sort of straight line. Oh, why is it deleting stuff? We'll get this kind of straight line fit, but we'll be missing these oscillations, which might not just be noise. They might be associated with seasonal effects and things like this. And so maybe choice 2, even though it's not perfect, is some kind of compromise. It'll capture a bit more structure, but maybe it won't overfit. So I would argue, actually, so I think what's been explained here is the sort of like conventional wisdom in statistics and probably does apply with a lot of standard training procedures. But what I'm going to argue in this talk is that we should actually go with choice 3. And in fact, choice 3 might be insufficiently flexible. And the reason that I like choice 3 is that I know that there's going to be some setting of the parameters, the AIs, which will get us closer to the ground truth function behind this data than could possibly be managed by choices 1 or 2. We just need a good way of learning these parameters that doesn't cause overfitting. Another perspective on this is to say that whenever you have a simple model which performs well, you ought to, in theory, be able to build a more sophisticated model around that simple model, which captures whatever it was about the simple model that led to good performance, but also captures some additional structure in data that will help make better predictions. So if we're trying to do handwritten character recognition, for instance, maybe if we try to capture irregular writing styles or weird ink blots on the page or something like this, we should be able to improve performance at least a little bit. And then in practice, we're actually finding, especially in modern deep learning, that we're using models with many more parameters than data and often finding that we get very good generalization. And so this has been perceived as quite mysterious. One of the biggest mysteries actually in modern machine learning. How can we use these models with tens of millions of parameters like a modern residual neural net on a problem with tens of thousands of data points like the CFAR10 image classification problem and find that we get such great generalization performance and don't really overfit despite the capability of the model to overfit. And I think a lot of these questions can actually be very naturally resolved from the probabilistic perspective, such that we can start even considering models with an infinite number of parameters and find that we get very good performance on problems, even with a very small number of data points. So at the very end, if we have time, we might consider things like neural nets with an infinite number of units and see what those models correspond to and how we can use them and how they can actually perform very well, better even in some cases than the finite neural nets. Okay, so before getting into that, I'll also talk a little bit more generally about uncertainty. So if I tell you to think about what comes to mind when I say Bayesian machine learning, actually, why don't we just do that? I mean, maybe tell me what you think of when you think about sort of Bayesian methods. What would be a defining feature? Bayes theorem. Probability, conditional probability. Right, so I think these are good answers. I would say priors are something that often people think about. It's like the Bayesian method is all about the prior somehow. Probability, definitely. Bayes theorem, yes. Continuous upgrade on model based on what happens. So you're you have this, what's called a posterior, and it's based on what's called a likelihood and a prior, and we'll introduce those things shortly. And as we observe more and more data, we keep updating our posterior. So there is kind of a natural online interpretation of Bayesian methods. Yeah, so these are definitely all associated with Bayesian methods. I would say that none of them entirely define what it means to follow a Bayesian approach. I would say that probably the key distinctive feature of a Bayesian method is this thing called marginalization versus learning, say, parameters by optimization, where with the Bayesian method, we say, well, let's actually consider, for example, all possible settings of these parameters in this model, like this 10,000th order polynomial, and make predictions using all of those models, and then weight each of those predictions by their posterior probabilities. So that's called marginalization. I would also say that uncertainty quantification is something that is very closely tied to Bayesian methods, and in particular, trying to quantify what's called epistemic uncertainty. So let's just talk about that for a moment. Now, sometimes people, when they think about, representing uncertainty, they think, okay, we're going to get better error bars and stuff like that on our approaches. And that is true. But representing uncertainty is also really crucial for making just even good point predictions. So even if you don't care about the error bars in the end, having a good representation of uncertainty when you're training your model is going to ultimately help you also make really good predictions. Okay, so uncertainty representation. So we've got what's called aleatoric uncertainty. So there are two types of uncertainty. There's aleatoric uncertainty, which is irreducible uncertainty. So can we think of some examples of this type of uncertainty? The weather, noise on data. Electron positioning. Yeah, these are good answers. So noise on data, I guess, is something that would typically be fixed. It's often assumed that we can't reduce that unless, like, maybe we build better equipment or something like that, but maybe there's some limit to how accurately we can make our measurements. So for instance, if we're looking at this CO2 example, maybe our instruments are only accurate up to a certain amount, and maybe this is based on some kind of fundamental physical limitations. So no matter how good we make our equipment, maybe we will only be able to make measurements up to a certain degree of accuracy. That would be an example of aleatoric uncertainty. Often in sort of games of chance, we're faced with aleatoric uncertainty. So if I say I'm rolling a dice, what's the chance it'll land 2? You'd say, oh, there's a 1/6 probability, and this is not something we can sort of reduce. Sometimes physical processes like radioactive decay are associated with irreducible uncertainty. This is a little bit of a physical debate. It depends a little bit on whether you're a determinist or not. And very smart people have kind of disagreed on whether the world is a deterministic place. So Einstein, for example, believed that if you knew the initial conditions of a problem to arbitrary precision and you knew the correct laws of physics, then you should be able to predict precisely the evolution of that system. Whereas there are others who, for example, have other interpretations of, say, quantum mechanics, et cetera, who would argue that actually there are aspects of the universe that are kind of fundamentally random. Like every time you make an observation, you'll get something drawn from some probability distribution. And so Einstein thought that that interpretation of quantum mechanics was fundamentally flawed, and he actually spent the rest of his life after general relativity trying to come up with a hidden variables explanation of quantum mechanics that would allow the world to be deterministic again. I'm actually sort of a determinist, I think. I think that it's a lot more intuitive than to assume that some processes are inherently random. I feel if you do that, then you have to give up causality in some sense, which is a big loss. But maybe we also get free will and stuff like that if we believe that there's sort of inherent randomness. So there is this debate, but in general, aleatoric uncertainty is for a given problem the uncertainty that we can't reduce, for instance, by gathering more information. So noise could be an example, maybe physical processes, some radioactive decay, maybe. And then there's this thing called, so there's a question, would a Kalman filter help with minimizing noise in the signal from the instruments? Yeah, so there are ways to try to help filter through noise, but then when it comes time to make a prediction about the next measurement that we'll have, that's going to fundamentally have this aleatoric uncertainty associated with it because the measurement itself is going to be noisy. So sometimes there's a little bit of a difference between trying to estimate some underlying ground truth function. Like we could say that there's some sort of like real function, I'll just draw it here, associated with CO2 levels. And everything that we're seeing here with the dots are just like measurements, noisy measurements of this function. And so we might be able to filter through the noise if we have enough data such that we get a better and better estimate of this underlying ground truth function. But then if we're going to make a prediction of CO2 in say 2025, we're only going to be able to validate that with respect to some kind of measurement we make. And that measurement is going to have that aleatoric uncertainty on it. So we're going to be sort of off in our prediction of whatever the measurement is by some amount. One might argue that all we care about is the underlying ground truth function, and I would agree with that, but there'll still be a discrepancy between our measurement and this ground truth function. Okay, so if we're correct about, say, our assumptions about how the noise are distributed, then we can sometimes filter through that if we have enough information. Okay, and then there's epistemic uncertainty. And this is what you might call sort of model uncertainty. So this would be associated with things like uncertainty over what the correct setting of those parameters are, the AIs, in these models. And so given what we've observed here, for example, with CO2, there are many, many different functions that will be consistent with those observations. So I drew one possible curve, but I could have drawn many others, and probably many of them would have looked very convincing given the information that we've observed so far, but they would be making different types of predictions. So this is reducible uncertainty. And it's associated with just lack of information. It's the type of uncertainty that we could shrink away to zero as long as we kept getting more and more helpful information. And so I would argue, sort of as a determinist, that most uncertainty in the real world is actually epistemic. Even things that seem like aleatoric uncertainty. So we can give a few obvious examples of epistemic uncertainty, like let's say you have a detective and they're trying to figure out sort of a suspect in some case. As they acquire more and more information, they should be able to have stronger and stronger beliefs about who the perpetrator is in this situation. And then maybe at the end, they're left with a little bit of aleatoric uncertainty associated with maybe the reliability of DNA tests, or whether they actually trust that footage hasn't been doctored or whatever. Like there's sort of this remaining sort of uncertainty that might be hard to reduce, but then there's a lot of epistemic uncertainty that is also reducible through gathering more information. And I mean, we've just also considered an example here, like as we get more and more examples of these points, we become more and more confident about which function generated those points. And if we had no noise on the measurements, then all of the uncertainty would be epistemic. But I would say even things that seem aleatoric are actually in practice may be epistemic. So let's say we're flipping a biased coin. Maybe our goal is to try to understand what is the bias of that coin. And in that case, the more times we flip, the better estimate we can make until we actually have no uncertainty about what the bias of the coin is. Even though every time we flip, once we know that bias, maybe there's some uncertainty about which side it will land on. And I would say the same, even applies, we can take it further with, say, rolling dice. So it might seem like every time I roll the dice that, there's an equal chance that it'll land on each side. But if we knew all of the physics associated with the problem, and we knew enough, like we knew the strength of each throw, we knew the friction on the table, we knew the wind in the air, we had a good physical model, then we should, in theory, be able to predict exactly which side the dice will land on each throw. And so a lot of uncertainty that seems irreducible is actually reducible, is actually epistemic uncertainty, as long as we're asking the right questions, as long as we have the right information. And Bayesian methods fundamentally are capturing epistemic uncertainty. And this will make a difference in many, many ways. So it'll make a difference in the quality of our uncertainty representations. It will make a difference in terms of the point predictions we are making. It will even make a difference in terms of what types of models we like to use. So from the Bayesian approach, we would like to use this third type of model, at least I'll argue that we would. But using sort of classical estimation, this third model would probably lead to overfitting. And so it'll really fundamentally affect how we think about model construction and generalization. Okay. And I guess as another high level comment, uncertainty representation is very crucial for using machine learning in the real world. So in the end, we try to use machine learning algorithms to make decisions. And it's very hard to make a decision if we don't have some sense of uncertainty associated with the predictions. For example, let's say we're trying to classify whether an X-ray image has cancer or not. It probably isn't sufficient just to have a model say, oh, well, it's cancer or it's not cancer. We would like to know, well, what is the probability that this image contains cancer? And what we do with that information will very much hinge on those probabilities because, for example, a false negative is going to be a lot more harmful than a false positive. And so there's kind of this asymmetric loss function that we want to combine with a probability distribution in order to make a good decision about what to do next. The same occurs, for example, if we have things like autonomous vehicles. The vehicle might need to know, where are the estimates of the lane boundaries around the vehicle and the distances to other vehicles. But in order to make decisions with that information, we also want really good estimates of uncertainty. I think it would be reasonable to argue that a point prediction in isolation is often completely meaningless unless we have some sense of the confidence around that point prediction. Because otherwise, what can we do with it? If our model is saying that there's a stop sign that's 5 feet in front, but the error bars are 10,000 feet, then that doesn't really help us do anything. It's no different than if it didn't make a prediction at all, essentially. But if it says it's 5 feet in front and the error bars are 1/10 of a feet, then that's very useful information in making a decision. Okay, so let's sort of think about first how we would approach things like that CO2 problem from a classical perspective. So the first thing we would do is specify some functional form for a model. And I'll just use X here instead of T because it's a little bit more general. So we might not just be considering functions that depend on time. We might also care about maybe something that is indexed by spatial location. If we're measuring, say, temperature as a function of latitude and longitude, and maybe we want to include time as well. Maybe X could even be like an image and we're trying to predict the class label of that image, or if we're doing what's called regression, what we were considering on the previous slide, maybe we're trying to predict, say, the orientation angle of the image or something like that. So we just got some general input X, and we're going to specify some functional form for our model. And that functional form will depend on some parameters. So I'll switch notation a little bit and call those parameters W. And for example, so this is just an example, we could have something like this is Wi x to the power of I equals 0 up to some model order, which I'll say J. But there are many other functions we could use, and this would also describe neural networks. Neural nets provide a different way of constructing a function, but we could still refer to it as a function that depends on some inputs X and its weights or its parameters W. Okay, and we want some way of learning these parameters given our observations. So let's sort of imagine that we're considering something like the CO2 example again. And I'd like you to tell me, how we might actually go about learning these parameters W, not necessarily from a Bayesian perspective, but just, any possible approach for trying to determine W from our data. So let's say we've got our data set D, which has a bunch of pairs of inputs Xi and outputs Yi. And the Yi's would be like the CO2 readings, and the Xi's would be like the times where we have CO2 readings. And we have n of these data points. So what I'm kind of looking for is an equation that we could write down that we could then use to try to learn the W's. If you're confused about something, also feel free just to unmute and ask a question. The gradient descent equation on F, something a little bit more basic. So gradient descent is an optimization procedure. Here, I'm just looking for the objective that we might want to optimize. Variance, least squares estimation. Maybe just go back to high school. So forget everything we know about statistics. If I just said, here are these CO2 points, and let's use the cubic polynomial, and then I want you to use that polynomial to make predictions, how might you specify the parameters of that polynomial? You'd first have to sort of write down some equation that you would be wanting to optimize. Maybe use weights on each point. So in this case, we just have maybe a cubic polynomial. So we have, for instance, f of x w equals w naught plus w1x plus w2x squared plus w3x cubed. And our goal is to learn w naught, w1, w2, w3 from our data set D. So D contains all the yi's, all the CO2 readings that we have so far at the xi's. So I'm going to specify some loss function, L, of W, and I want to minimize this, f of x minus y. Yeah, so this is kind of what I'm going for. We might have to make a few decisions along the way, but I'll give an example of a loss function that we might want to use. So we could say, well, let's measure the difference between what our function gives us at all the xi's in the data set, so all the times where we have, say, CO2 measurements, and the actual measurements themselves. And so let's take a sum of those differences, and maybe we'll take the squared differences. So let's say f of xi and w minus yi squared, and we'll sum from I equals 1 to n. So this takes all of the data points and sums the squared differences between the output of our function at those times and the actual CO2 readings. And if we minimize this expression with respect to w, then that will try to get f to match the y's as closely as possible. Does that seem reasonable? Does anyone have any questions about that objective or have any suggestions for maybe a different objective that we might use? Isn't this the LSC? Yeah, it is. So is there something else we might want to use? Like I've made a few decisions here, and they might be kind of arbitrary. Can someone maybe point to one of the properties of this loss function that we might want to change or kind of consider depending on the situation? We'll minimize with respect to W. So W here is kind of a vector that contains all of the different parameters. In some cases, we might be able to do this exactly. In other cases, we might have to use something like gradient descent to try to minimize this expression. Okay, so I've chosen the squared difference here. I could have also considered alternatively, I could have considered, so I'll call this the least squares. We could have done, or maybe I'll call it mean squared error. It's not really mean squared error, it's kind of just squared error. because we're adding all the squared errors up, but we're not dividing by n. So we could consider, for example, the absolute error, which would just be the absolute value of the differences between the outputs of our function and the yi's. Can anyone tell me maybe a reason that we might prefer one of these objectives over the other? An LSE would increase the weight on each difference. Positive and negative differences don't influence the result. That's true. That's true for both of them. One is differentiable. So these are all good observations. So the first was that an LSE, so the squared error here, would increase the weight on each difference. So let's say there's a big difference between f and y, then squaring it will make it even bigger. And so we'll really penalize sort of outliers in a sense, like our function not closely matching one of the yi's at a given point. Although I guess if it's small, then it'll be even smaller. So it still has this effect of sort of not caring so much about small differences and really caring about big differences. But if we care about big differences, if we decide we care a lot more about big differences, why not to the power of 4 or something like that? Why just squared? And this starts to get a little bit tricky. I mean, most of us probably would have a hard time saying why not to the power, like, justifying why we're doing it squared or something like that. Why can't we just omit outliers from our calculations? Well, it depends on what we mean by outlier. So outlier could be a very weird data point, and we might want to throw that away before we start estimating our model. But if we do that, we could also be throwing away potentially useful information from making predictions. Like, even though it's an outlier, maybe it still gives us some little bit of information that's helpful as long as we've got the right model. So it's a tricky thing. And I mean, this is something that statisticians grapple with quite a lot. And I guess in this case, yeah, the square or raising this to some kind of power would really want f to match y. So if some y was kind of very different than all the other y's, we're really going to try to fit that in that case. In the absolute error sense, yeah, there's some good observations. A bit harder to differentiate. There are things we can do to get around that in most practical instances. There's an observation that positive and negative differences don't influence the result differently. That's true for both these, and that's a great point. This sort of also just comes down to the context of our problem. And maybe in some cases, we really care if we underestimate CO2 more than if we, say, overestimate CO2. And so we might want to think about all of these things in specifying our loss function. But it's a little bit ad hoc and difficult. And as you might be able to predict, not something we need to worry about as much from a probabilistic or a Bayesian perspective. What if we took the log of the power? We could do that. I mean, why would we want to do that? I mean, it might sort of reduce the effect of the outliers. So I mean, that could be sort of another way of thinking about it. I guess in the end, if you take the log of an objective function, well, actually it wouldn't, because it's going to have the same, like if you have some function that you're minimizing or maximizing, and then you take the log of that function, you are going to get the same answer for the parameters that minimize that function. Yeah. But actually taking the log is often something that people do because it just makes other computations more convenient. Yeah, so log is what's called a monotonic transformation. So that sort of means that it won't sort of change, for example, the location of the different local optima. Mhm. Okay. Right. So let's sort of consider a different approach. So we could consider what's called the probabilistic approach, which specifies what's called a generative model for our observations. So the idea is that we have, or not y of xw, we have sort of our observations, y of x, which are generated from some noise-free function, f of xw, plus some kind of noise. And so we have different choices for how we could specify this noise. So I could say that this noise is, say, normally distributed. If you've seen the normal distribution, this is just a bell curve, and it's got some mean and some variance. And so we could assume that the mean is 0, and the variance is, say, sigma squared. So that would mean the measurement noise is sort of symmetric. And what this equation is telling us is that in order to generate our observations, we first sort of plug in the corresponding times, or x's, into our f, and then we get the output of our function, and then we add to that some kind of aleatoric uncertainty, this measurement noise, epsilon, and that gives us our y. And so this isn't Bayesian yet, this is just probabilistic. This gives us a way of specifying what's called the likelihood of all of our data. And so this is basically a probability density for all of our points. And so we can say, well, what is the probability that we would sort of have all of these data points under this model? And this is given all the x's. So this is our likelihood. And if we assume that given the parameters w, this is also given w as well, given the parameters w, that the points are independent, which is a reasonable assumption. I think not given w, of course they're not independent, because then we would just have no structure in our data. This would all be noise. We wouldn't be able to model anything. But given w, we assume it's independent. Then what we get is a product. So I'll say independent and identically distributed given w. We get our product from I equals 1 to n of p of yi given xi and w. And in this case, that's going to be a Gaussian density. And it's going to be, so the random variable here are the yi's. And the mean, in this case, just looking at equation 1, if we take the expectation of both sides, the expectation is a linear operator, which in this case means that if we have a sum of two terms here, it's going to operate separately on those two terms, and we'll just add the result. The expectation of f is just going to be f because it's not a random variable so far. And the expectation of epsilon, by definition here, is just going to be 0. And so that means the mean of equation 1 is just going to be f of xi w. And the variance, we can do sort of something similar and say that that's going to be sigma squared. So this is our likelihood. This is basically the probability of generating all of the points that we observed under this model in equation 1. And we can unpack this a little bit further. So I equals 1 to n. We can write down, well, what exactly is this Gaussian density? So it's 1 over the square root. This is just the equation for a bell curve. Sigma squared times the exponential of minus 1 over 2 sigma squared of f of xi w minus yi squared. All right. Any questions about that so far?
Hi. Hello. Hi.
Hey.
Can I ask a question?
Of course, yeah.
Yeah. So you used this random error here to generate the y's, right?
Mm-hmm.
and then you use that to calculate your likelihood.
Mm-hmm.
So let me see if I understand. When you calculate a likelihood, if you graph that, what is the, I don't know, I didn't understand what exactly is that. Is it like an area in the graph in which any point can be?
I guess a graph net would be like a neural network operating on a graph rather than on this type of.
I'm just asking if you print the output of this model.
Mm-hmm.
So P, so you have Y,
Mm-hmm.
you're adding the error. So
Mm-hmm.
each of the Y's will have a random error. And then when you add all the Y's, you have all the normal curve within your data, right?
Mm-hmm.
And then you're calculating the likelihood of all the pieces of the points together.
Mm-hmm.
So I am not very familiar with this topic, but I understand when you have a graph, you plot a line and you say, well, these are my predictions, and this is the interval. I forgot the word for that. Sorry.
Confidence interval.
The confidence interval, so that I understand. So the likelihood, is it anything like that?
So it's related to that. So the basic assumption here in equation 1 is we have, let's say, our data points, y indexed by x, and so we have some points here, and we have some f of x, and then we assume that these points have been generated by querying f of x at those x's here, plus sampling from some normal distribution with some variance sigma squared. And so these arrows basically are given by whatever samples we get from this distribution. So in some cases, maybe we are quite close. In other cases, we're a little bit far away. And if sigma is very large, then generally there'll be a bigger discrepancy between the dashed curve and the data points that we observe.
Okay. So this is, so in the end, you're just generating a more, a new model. It's just a new model for the prediction.
Yeah, so I guess this dash curve is conditioned on knowing the parameters W. So for every setting of parameters, like let's say I'm using the cubic polynomial, if I specify W0, W1, W2, W3, then I can just draw that function for any value of X. And then the assumption in this model is that these data points have been produced by that function plus noise drawn from a normal distribution at every point that we've measured. So the normal distribution could represent, for instance, things like the measurement error of our equipment. And so for any given W, we'll have a different curve, but the assumption is that given W, the parameters of our function, this is how we generated the data. We have this sort of functional form, which is sort of the true description of how, say, CO2 evolves with time. And then we have our measurements, which are generated from that plus noise.
Mm-hmm. Okay.
And so that noise, our sigma, will affect the error bars on our predictions in the end. So if sigma is very, very large, then we'll have more uncertainty in our predictions. Okay. And so we can use this expression in equation 1 to derive this likelihood, which I'll write as equation 2. And now I'd like to ask you a question, like, if we follow this approach, if we maximize this likelihood with respect to W, so this is called maximum likelihood, where we try to find the parameters W, which make it most likely that we drew this sequence of observations under our model, are we going to get a different answer than if we use the squared loss function? So you might need to do a bit of manipulation. You might even need to do something that someone had suggested at the end of the last slide. So let's think about that. So I said if you take the log of an objective function, that you'll get the same, like if you're optimizing that, you'll get the same setting of parameters. And so let's take the log of this expression, this product. And so we're going to get basically log of exp minus 1/2 sigma squared f of xi w minus yi squared I equals, or sorry, log goes inside here. And when we take the log of a product, we can turn that into a sum. So we've got the sum of log 1/2 pi sigma squared plus the sum of, this is from I equals 1 to n, of log of this exp. And so log and exp are sort of inverses of each other, so they'll just cancel out, and we'll get minus 1/2 sigma squared sum from I equals 1 to n of f of xi w minus yi squared. Okay, so we can see a parallel here with the expression we had on the previous slide. If we're just looking at this in terms of w, like let's say we fixed sigma and we want to optimize this with respect to w, we can see that maximizing the likelihood here will be the same as minimizing the squared loss. At least it'll give us the same answer for w. Does everyone see that, or does anyone have any questions about that? The reason being we still have a sum of squared differences between f of xi w and yi here.
Is there ever a point where the log, the sum of the logs 1/square root and 2 pi sigma squared is surpassed by the difference of the variances?
So where this first term somehow is surpassed, you mean that is much less than the second term, or?
Yeah.
Yeah, it could be. If, for example, we've chosen an f that isn't capable of fitting the yi's very well, that could be possible. So I would say, if we're just interested in estimating w, we don't immediately gain anything over the squared loss approach. We do get the ability to also estimate sigma, and if we believe that we've chosen a reasonable f, then that's kind of nice. It gives us a sense of the aleatoric uncertainty. But I would say the key advantage so far in following this approach is we now are making much more interpretable design decisions. We've basically derived the squared loss. Before, we just said, oh, so we have some function, we want it to fit these data points, we'll just sort of pull some loss function out of the air. We don't really know if it's what we want. But here we sort of had this assumption saying, okay, well, there's probably going to be Gaussian, or also known as normal, measurement errors. And when we do that, then we kind of derive the squared loss function. If we had assumed, for example, that maybe we have outliers in our data, so maybe there are some points that are very, very noisy, then we could have used what's called a heavy-tailed noise model, like a student's t-distribution or something like that, or what's called a Laplace distribution, which basically spreads its density. Yeah, that's where squared loss, that's exactly how we derive squared loss. And so that sort of means that there's going to be some sort of density for really extreme values in something like the Laplace distribution. And if we use that as our noise model, then we recover the absolute loss function, which is actually very intuitive because the absolute loss function is not going to penalize outliers as much. And that's because our probabilistic model is saying, well, there are some values of the noise which are going to be really large. And so we're probably going to have to be careful if we see some data point that's very different from all the other data points, then we're going to have to be careful about like not trying to fit that too closely. And so this probabilistic approach basically gives you a mechanism for deriving different loss functions, starting from more kind of fundamental assumptions. And so immediately we get a lot of value there in terms of model construction. But so far, we've only been accounting for what's called aleatoric uncertainty. We haven't captured the uncertainty in the parameters W. So let's think about how we might do that. We have this sort of observation model that says that if we condition on our parameters W, our data is a Gaussian distribution in Y, and its mean is f of xw, and its variance is sigma squared. Now, the next step is to try to represent uncertainty over W. So we can specify W as also coming from some kind of distribution. And we've got a lot of flexibility over what that distribution might be. So we could, for example, say that it's Gaussian and it's got some other sorts of variance. So W, in this case, I'm using to represent all of the parameters. So it's actually a vector value random variable, which is why my Gaussian distribution here has what's called a covariance matrix. So this is equivalent to saying that each Wi has a univariate normal distribution with mean 0 and variance alpha squared. That's just one example. We could use whatever distribution we like, and we can even represent the notion that we have no idea what would be a good setting of W. So the way that we would do that with a normal distribution is just to make gamma here super large. And that would probably be a good assumption. Like that would sort of help us in being able to make some reasonable predictions. Okay, so this is sort of representing our epistemic uncertainty. Then what we can do is before we had our likelihood, which I wrote down on the last page, we can sort of write this down, which was the product of all those normal distributions. We can write that down in short form as the probability of our data D given our parameters W. So this is our likelihood. And then we can multiply by our prior. And Bayes' rule says that this is going to be proportional to our posterior distribution over W given D. So we can actually just write down the full thing and say, okay, that is going to equal P of D given W times P of W over PD. And this numerator here is equivalent to P of D and W, the joint distribution over D and W over PD. And so PW here is the prior. PD is kind of a normalization constant, so it doesn't depend on W. We could call it what's called the marginal likelihood, and I'll explain where that comes from in a minute. And so just to back up for a minute, all you really need to know to do Bayesian inference are two very simple rules of probability, the sum and the product rules. So the sum rule says that if you want to find the distribution over, like let's say you have a joint distribution over two random variables, A and B, and you just want to find what's called the marginal distribution over A, then what you can do is you can sum out all possibilities for B, and then you'll get this marginal distribution. And so we could have two different quantities, like the probability that it will be sunny tomorrow, or that sort of random variable associated with that, and the probability that I'll be happy. And maybe these two things are related in some way. But if I just want the probability that I'll be happy, then I can sum out from this joint distribution over both these quantities all the values of the sort of what the weather will be like tomorrow. And then we have the product rule, which says that the joint distribution over two variables is equal to the product of the conditional distribution of A given B times PB, and that's also equal to P given A, PA. So you can actually derive Bayes' rule, which is just what I've written here. Like this whole expression here is just an instantiation of Bayes' rule, where W and D are random variables. We can sort of derive this from the product rule. So let's say I multiply both sides of this equation that I've just written a box around by PD. Then basically this is saying that the joint distribution, like PW given D times PD equals PD given W times PW. So that's just the product rule. So that's saying PW and D is equal to PD and W. And I've also applied the product rule here to go from this expression in the middle to the expression on the far right here, where I've got PD and W over PD. So these two identities are things that will frequently apply when we're deploying Bayesian inference. Okay, so I've written down the posterior distribution over W given our data. So that is like basically, really what we're interested in, at least as far as the parameters go. That is saying, if we observe some data, what are my beliefs basically about what the parameters could be? And this isn't saying, the parameters should be exactly this or that. It's giving me a whole distribution over what the parameters could be. So the parameters could have many possible values, and there are different posterior probabilities associated with those values. So this is just a function. It's a probability density. And in many cases, we could plot it. So if we wanted to look at maybe one component, like a particular WI, this would give us some distribution where we would say WI is on some axis, and then we have some sort of posterior distribution over what values WI could take, given whatever we've observed so far. Okay, so we can take the log of P of D given, of P of W given D, and that will equal the log of P of D given W plus the log of P of W plus the log of, minus the log of P of D. And if we like, we could try to optimize this expression with respect to W. And if we do that, then we're not going to care about the PD term because that doesn't actually depend on W. And so, why am I getting confused? Okay, yeah, there we go. P of W. Okay, so basically what we get is what we had before, where this is the likelihood, log likelihood, and this is the prior. So basically this term will be affecting our optimization in some way. So if I had specified P of W as this Gaussian distribution, then we would get some term here, which would look like a minus sort of W transpose W, sort of the dot product of our parameters scaled by this gamma parameter. So if gamma is super large, then this term disappears. And basically what this is saying is we don't want to make our parameters very large. So there's going to be a penalty for that. And so this is called regularization. It's actually L2 regularization. And this is designed in classical statistics to help avoid overfitting. And so if we went back to the squared loss function of the maximum likelihood, and I said, well, what's an issue with this approach? Probably we would say, as we did at the beginning when we were considering the CO2 concentrations, well, overfitting. If we choose a super flexible F, then we might have very little error in matching the Y's that we've observed, but then not very good generalization. And that's maybe because we have like, we're not respecting Occam's razor in some sense. We have too much complexity in our approach. And so in order to combat overfitting, people introduce these things called regularizers. And so this is an example of a regularizer. And often people sort of pull it out of the air, like I mentioned before with like the squared loss function, but we can also derive various regularizers, again, through a probabilistic approach. So the regularizer that we get using L2 regularization is the same as what we would get if we were to use a normal prior over the parameters W. And so that gives us some interpretation. It also gives us a way to construct other regularizers. So this is totally analogous to the situation where we were considering different noise distributions and we constructed different loss functions. Here we're considering different distributions over the parameters W in our prior, and that will give us different regularizers. So this isn't Bayesian yet because we're still doing optimization. So this is just regularized maximum likelihood optimization. But by using Bayes' rule, we get some interpretation of what different regularizers actually correspond to, what they mean. And we get kind of a recipe book for creating new regularizers, which is nice because otherwise it would be very hard to interpret, well, why do we want the weights to be small? Like, doesn't that seem kind of arbitrary? It's certainly hard to sort of reason about in general. And so we can get some intuitions about this in thinking about how to specify our regularizer. But this isn't fully Bayesian because we're still sort of betting everything on one setting of the parameters W. So that in the end doesn't actually account for the epistemic uncertainty in W. So the question is, how do we actually make predictions using a Bayesian approach? And the answer is to use the sum and product rules of probability. So if we want the probability of our output Y given any arbitrary test input, which I'll denote as X stars, this is wherever you want to make a prediction. So it's at any particular time, any spatial location for any image, and your data. So we've observed our data, that's the information we have, and we know where we want to make the prediction. And so we want this distribution, basically. The sum and product rules of probability say, well, you should first write down your predictive distribution given your parameters, your inputs, your data, and multiply that by the posterior over your parameters given your data and integrate with respect to your parameters. And so this might take a second to unpack, but let's do that. It's actually a lot simpler than it might look. So this first part, P of Y given W, is really just what we had before. So when we were making the assumptions that we had on the previous page, this is just a normal distribution, and its mean is going to be F of X star and W, and its variance is going to be sigma squared. And P of W given D is also something we can just write down. It's just going to be our likelihood, that big expression we had before, times our prior, and then times like a constant. And so this is something that we can figure out. And if we make those assumptions that we had on the previous page, that's also going to be a normal distribution. And now if we're given our parameters W, we don't actually care about the data anymore because our model is totally specified by the parameters. The parameters are things we learn from the data, so we can kind of cross out the data here. It won't change anything to include it, but we don't need it if we have the parameters. And so this is basically just saying, okay, well, this is the product rule for getting the joint distribution over Y star and W given X star and D. And we're integrating with respect to W. So this equality follows from the product rule. And then we can use the sum rule to say that this is just going to be P of Y star given X star and data, because we've got this joint distribution over Y star and W, and we're summing over all possible values of W. Okay, so this is the mechanics of how we compute this distribution. Now the interpretation. So if we look at this expression in the top line here, what this is saying is that we want to make predictions using a particular setting of parameters W, and then we're going to weight those predictions by the posterior probabilities of W given our data D. So we're basically summing over the predictive model that we had in the classical framework for all possible settings of the parameters. And then we just weight each of those different models by their posterior probabilities. So there's no optimization happening here. There's no overfitting because there's actually no fitting that's happening at all. We're just updating a distribution over our beliefs. And so this is properly capturing epistemic uncertainty because for each different W, we've got a different function. So we could imagine having our data points here. And for a particular W, maybe we get this fit. So this is, say, corresponding to W1. And then, or maybe that's a bit confusing. So this is a vector of parameters W. And then for maybe a different setting of parameters, we have this fit. So this is for W2. And then for a different setting of parameters, we have this fit. So this is for W3. And given the data points that we've observed so far in crosses, maybe we don't have that much information to distinguish between these different fits. Like maybe we have some sense that one is a little bit more probable than the others, but probability theory just says, let's actually combine all of these models together to make our predictions. And when we do that, we'll get a much better representation of uncertainty, because even if we believe that there's absolutely no noise at all on these X's in our measurements, we're still going to have uncertainty in our predictive distribution, which is associated with not knowing exactly which was the right function to fit the data, given what we've observed so far. And that, of course, is going to be an extremely important source of uncertainty. And we know that it's going to have certain intuitive properties. So if we assume that there's no noise on the data, then all of these functions that I've drawn with the dashes would have to perfectly go through all of the X's, because our assumption is that they're noise free. And so we ought to actually have zero training loss on those points. But as we move far away from the data points, there ought to be quite a variety of different functions that are consistent with our observations. So we should have a lot of uncertainty there. So if I kind of redrew this plot, and instead I was drawing the Bayesian predictive distribution, assuming no noise, that's a little bit different than in the top plot here. What we would see is there would be sort of big uncertainty away from the data and growing, and then very little uncertainty towards the data. And at any given point, like let's say I want to make a prediction at this X star, we will have a predictive distribution, and it'll have some mean, and it'll have some variance associated with it. And we can sort of pose a question like, what is the interval that will give us a 95% probability of capturing the truth? And that will give us sort of some natural error bars on making our predictions. So what sort of interval do I have to consider around this mean here to capture 95% of this distribution, which I've drawn kind of flipped on the vertical axis? And so that is kind of the essence of the Bayesian approach. And when we follow this approach to making predictions, we can then really embrace flexibility. We can use models with many, many more parameters than data and reliably not overfit, because we're actually doing what probability theory tells us to do. Overfitting, in a sense, is an artifact of ignoring epistemic uncertainty, ignoring an obvious source of uncertainty in our modeling. And as we get more and more and more and more data, our posterior around our parameters will become more and more concentrated. So initially, maybe when we don't have very much data, we have this very sort of flat distribution around what would be a good setting of the parameters. Maybe I won't draw it on the X here. Let's do it. We'll have this sort of like initially, maybe like we sort of have some candidate for our W, which I'll call W prime. And maybe that's the mean of our posterior after we've observed some stuff, but maybe we're pretty uncertain. Like there are lots of other values that it could take. So this is P of W given D. And then maybe we observe some more data, and then it's like, oh, well, actually, there's a lot of evidence that it's this setting of parameters, W double prime, that provides a really good description of the data. So maybe now, in the first case, maybe we have n equals like 10 points. Maybe over here we have like n equals, 100,000 points or something like that. And so we're updating our sort of mean for the setting of parameters, and we're also becoming super confident. And as we get more and more and more data, this distribution will just start to collapse along a specific setting of parameters W. And that will eventually then give us the same answer as the maximum likelihood approach, because at that point, the likelihood will sort of dominate and the prior won't really have very much of an effect anymore. So I'm going to sort of conclude with an example that will kind of put all of this stuff together. Okay. So let's suppose that we are flipping a biased coin. So let's move away from regression just to have a bit of variety here. And so let's suppose we flip a biased coin with probability. I think this might blow your mind, so just bear with me for a moment. Probability lambda of landing tails. Now let's consider 3 questions. What is the likelihood of a set of data D equals Y1 up to Yn? So these are all the flips we have. 2, what is the maximum likelihood solution for lambda? And 3, suppose the first flip is tails. What is the probability that the next flip is tails using maximum likelihood? Okay, so just look at these questions for a minute and maybe write them down and think about them, just using what we've introduced so far. And I'll sort of proceed in formulating a solution. So the likelihood of the data, so we have a sequence of flips. We could represent them as, say, 1s and 0s. So this is often sort of a convenient thing to do when we're sort of trying to translate a high-level problem into a mathematical expression that we could then use to get an answer. So let's just make our lives easier and let yi equal 1 if tails and 0 otherwise. Then our likelihood is going to be the probability of getting this sequence of flips. So we'll get a sequence of 1s and 0s. And the probability of getting a tails is lambda. So we're going to get lambda to the power of yi, because we're going to get yi. If yi is 1, it's going to be tails. So that's going to be multiplying by a lambda. And probability of heads is 1 minus lambda, and then 1 minus yi. So we can just imagine if we have, like, let's say 2 tails and 1 head. That means we're going to see 1, 1, 0. So that's going to be lambda squared times 1 minus lambda is our likelihood. These are assuming that these are independent, basically, given lambda. Okay. If we don't care about the order, then we can just say that this, if we don't care about order unimportant, then we can just say that the likelihood of getting m tails is given by a binomial distribution. All right, so there, we've got our likelihood. What is the maximum likelihood estimate? So this is something we can compute. So if we want to take logs and differentiate and set the derivatives equal to 0 and check that that's indeed a maximum. So this is sort of something we do a lot in first year calculus. We can work out, and I'll just write it down, but it's actually, I'd encourage you to go and work this out, that the maximum likelihood, so basically the lambda that maximizes this expression, is equal to, so we can write that as argmax over lambda of P of D given M and lambda is equal to M over N. So in a sense, this is intuitive. It's saying that, let's say we flip the coin N times and we observe M tails, then we're estimating that the probability of getting tails on any given flip is M over N. But there's actually a bit of an issue. So let's consider question 3 now. Let's suppose the first flip is tails, and we wanted to use this framework to estimate that the probability that the next flip would be tails. So if the first flip is tails, then N is 1 and M is 1. And so our estimate for the bias is that there's a 100% chance that we'll just be getting tails. And so that means that we predict on any subsequent flip that we're going to get tails. And I'd ask you, is this actually something that you believe? Like, do you think that that's reasonable? Like, if I just said, I've got a biased coin, I'm not telling you what the bias is, and I want you to guess what it is based on the flips that I'm making, and I flip it once and it lends tails, would you say, yes, there's a 100% chance that you're going to get tails on every subsequent flip? Surely not. And this is sort of a consequence of following a procedure that does not represent our honest beliefs about the problem and ignoring epistemic uncertainty. And so let's think about how to estimate this from a Bayesian perspective. So we've got our likelihood, which we're writing as P of D given M lambda equals N choose M lambda to the M 1 minus lambda to the N minus M. If we choose a prior of the form lambda to the A times 1 minus lambda to the B, and we multiply that against the likelihood, then we'll get a posterior that has that same functional form. So you don't sort of really need to know this in the context of this example, but that's called a conjugate prior. So when you have a prior and you multiply it against the likelihood, and then the corresponding posterior has the same sort of functional form as the prior, it'll be lambda to some power times 1 minus lambda to another power in terms of lambda, then that's said to be a conjugate prior, and that's kind of convenient. And there's a distribution in probability called the beta distribution, which has exactly that property. And so it's equal to gamma A plus B over gamma A, gamma B times lambda to the A minus 1, 1 minus lambda to the B minus 1. So this distribution is defined for lambda between 0 and 1. And these coefficients here, these gamma functions, are just so that this is normalized, so that if we integrate this distribution over all values of lambda between 0 and 1, then the answer will be 1. So it's really conceptually not that much different than this distribution I wrote up here. It just is normalized. Okay, and we can compute the expectation of lambda. It's just going to be A over A plus B in this model, and the variance of lambda is going to be AB over A plus B squared times A plus B minus 1. So there's a question then of how we should specify this prior. So the beta distribution is actually very, very flexible. If we, for example, choose A equals 0.1, B equals 0.1, then we get something that looks a bit like this. This is 0.5. So that would mean we think it's probably quite biased in some direction, but we don't know which direction. If we use, so this would be for A equals 0.1, B equals 0.1. If we use A equals 1, B equals 1, then it's just a uniform distribution between 0 and 1. So this will, of course, integrate to 1. If we use A equals 8 and B equals 4, then we'll get something that's sort of a bit skewed past 0.5. I would say in the absence of additional information, a good prior here is just, I don't know what the bias is. We have no reason to believe that it's, biased in one particular direction more than any other. And so let's just use this uniform distribution over P lambda. Okay, so we can then write down our posterior. So that's just going to be proportional to our likelihood times our prior. And we can actually write this down. It turns out that this is a beta distribution because of this conjugate prior property that I mentioned. And it's going to be over lambda, and its mean is going to be, or its parameters are going to be m plus a and n minus m plus b, where n is the number of flips we've done, m is the number of tails we've observed, and a and b are the parameters of our prior. So if we're using that uniform prior, then that's a and b are just going to be 1. And what we can do then is compute, well, what is the expected value of lambda given our data? And so this is really using the sum and product rules. This is kind of the predictive distribution that we want. So this is lambda, p lambda given d, d lambda. So this is saying, okay, well, if we have all these different, we have sort of a posterior distribution over the different values of the bias. So let's sort of average over all of those different values. And lambda is just going to be our guess for the next flip. So that's like our predictive distribution that we had in the regression setting. Then this is going to equal m plus a over n plus a plus b. And so if a and b are 1 in that example, then an m and n are 1, then we've got 2/3 chance that the next flip is going to be tails, which seems more reasonable. I mean, probably we couldn't have a strong feeling that that's, in disagreement with our intuition. And as we get more and more flips, we can see that m and n are going to dominate here. So the data is going to dominate and the prior is going to disappear. If a and b are very large, then we've got a strong prior belief about something. And I'd like to also emphasize that this is very different than regularized optimization. So if we had optimized this expression, this posterior here, we could say that that's taking log of pd given lambda plus log of p of lambda. If p of lambda is uniform, then of course it doesn't depend on lambda, and it's not going to affect our optimization answers. So there's a very important conceptual difference between fully Bayesian inference and regularized maximum likelihood optimization, where the regularizer, say, comes from a prior. The difference mechanically is with the Bayesian procedure, we're actually doing this Bayesian model average, which is given by this integral here. In the optimization procedure, we're still kind of ignoring epistemic uncertainty and betting everything on one setting of lambda. And in this case, if lambda is uniform, you won't even get any regularization in that setting. You'll get exactly the same prediction as before. Whereas if we do the integral, we do make a very different prediction. All right, so there are many other kind of examples like this that we can make, and they all basically drive home the point that the classical estimation procedure, once we dig into it a bit, is actually pretty irrational, and that's why we have to conjure up concepts like overfitting and so on, and then try to sort of put some band-aid on the procedure like regularization to protect against overfitting and so on, because it all kind of boils down to an estimation procedure which doesn't represent our honest beliefs about epistemic uncertainty. And when we do that, it turns out we can actually use infinite models very naturally, and these models are extraordinarily flexible. They're even what's called universal approximators. They can approximate any solution to arbitrary precision given enough data, but they tend to work very well and also generalize particularly well quite often when we have a small number of data points. And so there isn't necessarily a trade-off between flexibility and being able to do well on problems with not very much data. That trade-off is mostly a consequence of classical estimation procedures. Okay, so that's the example. Any questions? Okay, so how does unstructured data affect the Bayesian approach? Is it necessary to apply some sort of normalization algorithms to bring uniformity to the data and get a better probability? So I assume this question is about like maybe what happens if we're not sure what we should use as our prior? Or were you asking something different? All right. Well, if the, yeah, okay. I would say if we're not sure what prior to use, then we're still going to do better by just specifying a prior that basically says, I don't know, which in the case of the coin toss example would have been that uniform prior. In the case of the regression example would have been, say, a Gaussian distribution over W, which had really large variance. And we will get a meaningfully different answer if we do the full Bayesian marginalization procedure. If we have some reason to believe that the parameters should have certain values, or we'd like to rule out other values, like let's say we, for some reason, think they're all positive or something like this, then we can also do that in our prior. And so that sort of provides a mechanism to incorporate additional knowledge about the problem into our modeling procedure. But if we don't have that knowledge, we can still represent the lack of knowledge, and that will lead often to better predictions and more intuitive model construction procedures, because we are actually capturing epistemic uncertainty, and that will come through in the Bayesian model average. Okay. So there's a question that says, so then why not use Bayesian probability instead of optimization if it's more robust? Well, yes, I think we should use Bayesian methods. I guess if the question is, well, why is it not always used in practice? I think that sometimes there are computational constraints. So we have to compute this integral in the continuous setting. And sometimes that integral is very difficult to compute and requires a lot of computation. And so one might sort of prefer the frequentist approach as an approximation or something like that under computational constraints. And we can actually view the classical approach as a special case of the Bayesian approach. So just kind of returning to the notation at the beginning where I wrote down my predictive distribution, I said y star given x star and data is equal to p of y star given w x star times p of w given data dw. If we approximate our posterior with some other distribution, q of w, which is basically just a point mass around the maximum likelihood solution, then we'll recover the classical procedure. And so if it's the case that the posterior is really well specified by the data, like there's a lot of information to give us a lot of knowledge about which setting of parameters we want to use, then the classical procedure will actually not give you a very different answer than the Bayesian procedure. Where they'll be very different is where the posterior is quite different from a point mass, and the different settings of the parameters give rise to quite different types of functions that we would want to use to fit these data. And so I would say that, probably the main deterrent to using a Bayesian approach is the computation associated with these types of integrals. But in many cases, it's actually quite feasible to use modern approaches to estimate these integrals, and quite often we'll get much better answers. And even if we can't compute the integral exactly, we can see from this correspondence of how the classical approach can be viewed as a special case of the Bayesian approach, where we have this approximate posterior, that we can probably still use a much better approximate posterior without a lot of additional expense and improve our answer. So maybe the posterior doesn't look at all like a normal distribution, but a normal distribution will still be more flexible in capturing some aspects of that posterior than a point mass. And so we could still improve our predictions, even if we can't estimate that integral perfectly. But I would say that, you know, in virtually all, I mean, in 95% of problems, it's feasible to at least follow an approximate Bayesian integration procedure and see much better performance than what you would get with classical estimation, even if it's regularized classical estimation. Okay, so the next question. In the expression for Bayes' rule, there was that marginalized likelihood term you mentioned. How would we determine that for the CO2 example? Okay, that's a good question. So the marginal, so we have basically our posterior equals our likelihood times our prior over our marginal likelihood. Now, in terms of making predictions, in many cases, we don't need to worry about our marginal likelihood, P of D, because it doesn't depend on W. So we can write down that our posterior is sort of proportional to P of D given W times P of W. And we sort of have our expression for PW, we have our likelihood, we multiply these things together. We say, oh, this looks a bit like a Gaussian or something, and then we can sort of write down a normalization constant and sort of use this for the purpose of making predictions. However, the marginal likelihood can become useful if we're trying to learn things like hyperparameters of the prior. So maybe the prior itself, like we saw in the coin toss example or in the regression example, has its own parameters. In regression, it was that gamma parameter, and in the coin toss, it was the AB. So maybe P of W is really P of W given gamma or something like this, or given maybe A and B. And maybe we want to estimate A and B. Maybe we don't want to just specify them, or maybe we want to put distributions over A and B, and those distributions have their own parameters and so on. So in this case, everything here is kind of implicitly conditioned on A and B, including the marginal likelihood. And so the marginal likelihood in this case, P of D given A and B, will be equal to the likelihood, D given W. The likelihood won't depend on A and B because once you observe W, you'll kind of block the dependence with A and B. There'll be this conditional independence. And I'd really recommend Christopher Bishop's Pattern Recognition Machine Learning Chapter 8 to kind of learn about these things like conditional independency and graphical models. It's a really beautifully written chapter and it's available for free online. But the integral will basically have this form, and this is just the sum and product rules of probability again. And this is something we can, in some cases, compute, and in many cases can approximate. And this gives us sort of another objective function for learning A and B. And this is actually a very useful mechanism for trying to estimate parameters of these priors. So let's say we have a prior over W and we're not exactly sure what it should be or what its parameters should be. We can also treat that as an estimation procedure. And the marginal likelihood would give us a mechanism for actually doing that estimation. In many cases, we also might want to do model comparison. So we might want to be saying, okay, we have our two Bayesian models, and we, in maybe one instance, want to know which one we want to use. Then we might want to compute, well, what is the marginal likelihood for model 1? And what is the marginal likelihood for model 2? And then we'll sort of compute the ratio of the marginal likelihoods, and that will give us a sense of you know, which model we should prefer. A really compelling property of the marginal likelihood is that it automatically has a sort of an Occam's razor effect built into it. And so, you know, there isn't really time to go in depth, but let's suppose we consider a conceptualization of all possible data sets on the horizontal axis and the marginal likelihood on the vertical axis. We could imagine that maybe we have a model which is super flexible in the sense that it can generate quite a wide range of data sets. So for the polynomial example, that would be like for different W's, we get different functions. Those different functions are the different data sets we can generate with our model, but it doesn't give very much probability to any one of those data sets. And then maybe we have another example where we have this sort of intermediate model, which is like, it has a few parameters and we have a distribution over those parameters. It can generate some data sets with reasonable probability. And then we have another model, which is like maybe just a linear function, like a0 plus a1x, then we just have a distribution over a0 and a1. That can only generate straight lines with different slopes and intercepts. So the marginal likelihood is a proper normalizable density, meaning that if we are considering those data sets, like the straight lines, then the straight line model will be able to generate them with much greater probability because this whole thing has to normalize. And what we can say then is for any given data set, like let's say we're considering a particular data set here, the marginal likelihood will automatically favor the model of smallest complexity that is consistent with our observations. And so we can see here that the simplest model here can't even generate that data set, so it's out of the running. The sophisticated model can generate the data set, but it doesn't generate it with very much probability. And then this intermediate model does generate it. Now, this might superficially seem a little bit at odds with my intuition at the beginning, saying we should always build the most flexible possible model. We should always build the most flexible possible model, but I would say that we don't want to conflate flexibility and complexity. Those two things are somewhat subtly different concepts. You can have a model which is very flexible, but it also assigns a lot of its mass to certain types of solutions. And so that would correspond to having sort of heavy tails on this diagram, but also a lot of kind of support, a lot of mass for certain types of explanations. And so, induct these things, that the sort of distribution of that support describes inductive biases. And so the marginal likelihood, in short, basically is a very powerful mechanism for model comparison. Unlike most approaches, it won't just favor the model that is automatically the most flexible. It will sort of have this Occam's razor notion automatically incorporated into it. And this is also related to concepts in information theory, like minimum description length. And so if you're interested in these things, I would recommend chapter 28 of David Mackay's book on information theory, inference and learning algorithms. And that will tell you a little bit about the marginal likelihood for model selection. If you're interested in sort of reconciling that with this notion that we should always build the most flexible model, then I would recommend both my PhD thesis, which is on my website, the first chapter, as well as a more recent paper that I wrote with my student Pavel Ismailov called Bayesian Deep Learning and a Probabilistic Perspective of Model Construction. Or of generalization. Okay. All right, nearly out of time. Any last questions?
If you could give us, do you have any sources that we could use other than these to get more of a foundation in the mathematics needed to understand Bayesian?
Yeah, so I would say my favorite resources are David Mackay's book, and I can provide links to the organizers who can probably share them. David Mackay's book on information theory, inference, and learning algorithms. Actually, I have it right next to me. So it looks like this. And it's also available free online, as well as Christopher Bishop's book, Pattern Recognition and Machine Learning. I would say maybe the first 3 chapters in chapter 8 of that book are especially useful. And then in terms of just the foundations of probability, et cetera, there's a book by Grimmett and Sturzaker, which is more of a math textbook about probabilistic approaches. It's not at all a machine learning book. It's more about things like conditional expectation and random variables and distributions and stuff like that. But it's a really nice kind of intro to probability book. I would say the Bishop book is probably a little bit hard to approach initially if you aren't a math major and aren't used to kind of taking lots of math courses every semester. But after reading it a few times, it does become very useful. And in many cases, if there's something that isn't immediately accessible, one can kind of look online and see if there's a better way to understand it. I would say that the Mackay book is probably a little bit more immediately accessible, but it's also less of a conventional textbook. It's more of like a reference book. Like it's got lots and lots of chapters and they're all very interesting. But it would be probably a bit hard to kind of read the book linearly, kind of front to end, whereas the Bishop book is more intended in that way. There's also the Kevin Murphy book, and it's nice, but it's also a bit encyclopedic. So they're coming out with a new edition, and I've actually helped in writing the new edition. And I think the first one is being released. The first volume of it is being released now, and I think it's available. And the original version was 2012. So it's good, but it's also it's kind of huge and sometimes has little pointers to a lot of different topics. So yeah, I would say all these references are good. I think I've heard very good things about the Fast AI courses as well, and they have courses on things like scientific computing, which help provide, I think, a good general foundation for machine learning.
I'm sorry, could you repeat the probability book one more time?
So it's by Grimmett and Sturzacker, and I think it's called Probability and Random Processes, but I would need to double check.
Sturzacker. Okay, thank you.
Do you ever feel the desire to go back to physics and try to unify quantum mechanics and general relativity? Well, I think those are very exciting questions, and I'm very interested in the answers. I mean, one thing I like about machine learning is it gives you a lot of flexibility to consider problems in other disciplines and in a very serious way. So I feel really kind of fortunate to be able to collaborate with physicists who are specifically interested in those kinds of questions and maybe bring something to the table through probabilistic modeling or sort of other approaches in developing machine learning methods for scientific discovery. And so I feel like that door isn't necessarily closed. And I have been considering sort of questions in physics, and I really do enjoy those types of problems. So maybe someday, we'll return to general relativity. And in fact, actually, we have been looking at, solving some of the partial differential equations in general relativity using machine learning methods. And so I think, yeah, that could happen.
Well, that seems like a good note to end it on. So thank you so much, Andrew, for the wonderful lecture and for staying extra, and all the other students for staying long. It's super interesting. I feel like I learned stuff from that. And yeah, so for the students, there are some ops hours ongoing.
Thanks so much, everyone.
If you still have questions about pretty much anything covered throughout the whole week or the labs, there's still office hours now. I think in the afternoon, there's our final lecture on fairness and ethics in machine learning. So make sure to attend that. And otherwise, I think now is lunch break. So we'll reconvene around 1, I believe.
Thank you. That was literally one of the best lectures I think I've seen so far. I really enjoyed the mathematics that you provided and the derivations. It was really, really cool.
That's great to hear. Thanks so much for coming. It's been a really great experience, and it's been nice to meet you all.
So see you all at 1.
Thank you.
All right. See you later. Bye-bye.